or you like maybe have 2 or 3 workstations. In the high bay, really almost a dozen, maybe at least 10 workstations. That's why the sort of width and length are more important, especially as we try to really get the production line going. We need more workstations.
Half a booster, half a ship.
Yeah, exactly. Yes. Well, we're using the ullage gas for attitude control. So instead of having separate attitude control thrusters, we're using the ullage gas itself for attitude or reaction control once you're in orbit. Or basically when you're in a vac, earlier design iterations, we had a separate cold gas attitude control system with nitrogen bottles, but that actually doesn't make a lot of sense since we've got a bunch of ullage that we're going to vent anyway. So might as well use the ullage gas, attitude control, and small delta V changes on orbit. The deorbit and the landing burns are done with the header tanks. So you actually want to vent the main tanks down to just above atmospheric pressure. You want to have enough pressure in the main tanks for structural stability, but not any more pressure than is needed for pressure stabilization for atmospheric entry. But when it gets to orbit, it's going to have really a lot more pressure than is needed for atmospheric entry.
Okay.
So we would in any case end up venting the main tanks down to the pressure needed for re-entry. So we'd be tossing that gas away. Might as well use that gas for attitude control and small maneuver. Even then, we'll still end up dumping the remaining gas that's not needed for entry. Yeah, actually, when you look at the old design, it's just like obviously it was pretty dumb to have a separate cold gas reaction control system. We have excess ullage gas. If we simply have main tank vent in the direction that you'd want, then there's no need to have a separate ullage thrusters. You can literally just use the vent. The hot gas thruster was definitely over-engineered and unnecessary. Just using ullage gas for small thrust, the obvious move. In retrospect, the obvious move. So it's a significant optimization, mass and cost savings to use the ullage gas for attitude and reaction control than to have separate cold gas thrusters. I'd say that's like one of the biggest improvements that we've made.
I gotta admit, that was when you were talking about that last time.
It occurred to me while I was explaining it to you. I was like, wait, what are we doing? We kind of went through this exercise for the ship, and then it's like, wait a second, we should do that for the booster as well. And that just occurred to me literally while I was doing the interview with you. So this is Joe Petrozalka. He's head of booster engineering. Experienced wind is hitting the cylinder of the vehicle, and then it's rolling around the cylinder, and it's kind of like losing pressure as it rolls around. Yep. By having the chines be not at 180 degrees, but a little lower down, we're catching more of that air that's escaping.
Okay.
And so technically you actually have slightly less cross-sectional area, but you have more integrated pressure at the base. These are very primitive chines.
Yeah.
We can do way better.
Our first attempt, and I expect to change them quite a lot over time.
But like if you say like what are optimized chines, you'd actually want them to get bigger as you get
wider at the bottom.
Yeah, wider at the bottom. We know how to use grid fins from Falcon 9. Grid fins are much more consistent than flaps as you go from hypersonic to supersonic to transonic to subsonic. So you're going through these different Mach regimes. Yeah. And grid fins are much more consistent than a wing or a wingy thing.
A wingy, yeah.
Especially as you go subsonic, the center of pressure on any kind of flat surface shifts significantly when you go from supersonic to subsonic. Could you be lighter than a grid fin? I think there's a good chance you could be. There's also another factor, which is the actuator power needed to turn a grid fin is much less than is needed to turn a wing, a sort of a wing-like thing. Especially as that center of pressure changes. So like we're not saying we're right. To be clear. Like we're definitely not optimal, but it'll work.
Yeah.
It's probability of it working is good, and it's one less problem to solve. It's also we obviously don't need 4. I think we could probably get away with 2. Definitely not more than 3. If you know your position well and you know your winds well, you can in theory have a ballistic arc when you do your boost back burn that is very accurate with nothing. And we tried this in the early days of Falcon 9. Any small asymmetries on the vehicle will cause it to go crazy, basically. It'll spin up and start flapping around, and it'll just start oscillating and rotating, and
dynamic stability becomes a concern.
Yeah. So technically, you don't actually need massive surfaces. You just need to be able to take out the asymmetries of the protuberances on the vehicle and any error that you have with respect to position or your boost back impulse. Control surfaces you need are actually not very big. We've shrunk the grid fins significantly from where we started out. They're much lighter, aspirationally 2 grid fins, but certainly not more than 3. And the third one can be small.
The liquid oxygen tank section for booster 8 is coming along very quickly right behind booster 7. And then the ship 24 nose cone. So this is the ship that we hope to pair with booster 7 for our first orbital launch attempt.
It's like we call it the Pez dispenser, and it's kind of like that. It's the Starlink satellites are, in this rack, which looks like a friggin' Pez thing, because they're like, kind of like rectangular, just like a Pez, and they're stacked inside the nose cone, inside the fairing. Since they're low profile, we only need really a small door. With a small door, we can use pressure stabilization, like we can retain pressure in the fairing, so we can at least partially pressure stabilize the nose cone or fairing. A small door weighs a lot less than a giant door. We are incurring some complexity for the sort of the racking system inside, because you've got to have a racking system. So it's more complicated than a Pez dispenser, but it's the general principle is
Is it
similar.
like spring loaded then, or hydraulically loaded or something, or?
It's electric. Industrial pallet stackers, it's the same basic principle. You're loading it in at 1G and then you're unloading it at 0G. You could have some situation where you're unloading a mechanism, and because you unload the mechanism, it now binds. That's hard to test for. I wouldn't say that there's like high confidence that the first flight will work. I think there's a good chance that it does not reach orbit, that there's an issue with the booster or stage separation, or with the ship doesn't start, and then even if it does get to orbit, there's the probability that the ship makes it down intact is also not super high. This is why it's entering over the Pacific, an unpopulated area. The thing that will happen, or should in theory happen here, is that when the tiles get hot, they will expand and tighten the gap. The gaps that you see here should be smaller when the tiles heat up. You're really not gonna see a lot of heat going down through those gaps, is our expectation. I mean, we'll be coming in at an angle similar to the shuttle, like, 60, 70 degrees. So sort of like if the ground is the surface of the Earth, we're sort of coming in like that.
Yeah.
For a reusable heat shield, we want to minimize the peak heat load.
Yep.
So the peak heat load is going to determine if we melt the tiles or not.
Yeah.
And if you melt the tiles, they're not very good for reuse. There's atmospheric density, velocity. You want to slow down as much as possible in the thin upper atmosphere. You minimize peak heating. Now, we're going to learn a lot from this first entry. We think we've learned what we needed to learn really with the suborbital flights.
Yeah.
And there wasn't really much to learn, so best to focus on getting to orbit. The Starship orbital stack is going to come off the pad very fast. It's got a high thrust to weight, 1.4-ish, maybe 1.5. For a reusable vehicle, you actually want to have a higher thrust to weight than an expendable vehicle, because thrust to weight below 1 is not doing anything.
Yep.
So your propellant is not being useful below a thrust to weight of 1. So you actually want to have a higher thrust to weight for a reusable vehicle than for an expendable.
Yep.
For an expendable vehicle, the cost overwhelmingly is in the vehicle itself that you are losing.
Yes.
But for a reusable vehicle, if it's rapidly reusable and completely reusable, the cost of propellant is the single biggest cost of the flight. And so you want to have a high thrust to weight so that more of the thrust is useful. This may sound sort of mercantile, but it's actually the thing to optimize for is cost per ton to orbit. Like, you can't cheat if you get cost per ton to orbit. Fully considered cost per ton to orbit. And any given technology is only relevant to the degree that it reduces cost per ton to orbit. For Mars or the Moon, minimize cost per ton to the surface of the Moon or to the surface of Mars.
Yeah.
And just to give you a sense of just how much we need to improve it, it's really insane. Like right now, the cost per useful landed ton surface of Mars is in excess of $1 billion. The rovers, it's really just the rover
Yep.
that is the useful thing.
Yep.
So if the rover weighs a ton,
Yep.
then and it costs $1 billion to get there, it's $1 billion per ton to Mars. Now, in order to make life multiplanetary, have a self-sustaining city on Mars, that number will have to improve to, I think, probably under $100,000 a ton. That would be a 10,000 times better than the current state of the art. To put things into perspective, how much of an improvement is needed? Not 10,000%, 10,000-fold. That's what Starship is intended to do. Be 10,000 times better than the current state of the art. We're not breaking any laws of physics. I think we probably shouldn't take pictures of the inside. Everything's going to have heat shield tiles. You see like a steel part at the base of but that'll have to have tiles on it. Well, we're building the mega bay, but anyway, right now the important thing is just to get to orbit with some reasonable payload. The thing that's like really counterintuitive about the Starship is that it's not an aircraft; it's falling. We're just constantly trying to brake, as opposed to an aircraft is trying to generate lift and fly horizontally. We are trying to generate drag and be as draggy as possible when we fall. It's a very different optimization than an aircraft. I mean, there's a custom-built tower with arms that are designed to catch the largest and heaviest flying object ever made and pluck it out of the air. I mean, that's the theory anyway. I mean, it's still super crazy. You know, at SpaceX, we specialize in converting things from impossible to late. But it's pretty nutty because you're gonna have this gigantic, booster coming back. I mean, that's 9 meters in diameter, not counting the chines, or roughly 30 feet in diameter. It'll weigh about 250 tons. Just a bit on the heavy side. We'll make that lighter over time. I mean, there's several tons of air mass in the vehicle. If you say like, what's the mass of one atmosphere in that volume? It's several tons. The velocity at which we start up the engines is more than half the speed of sound. So this thing is still coming in really fast.
Yeah.
Pretty much down in a downward direction. So then to light the engines, like I said, I think around Mach 0.5, give or take, several hundred meters in the air. So it's got to slow itself down very fast, correct any error, drop the velocity to basically zero, come in between the arms. The arms will be wide, and as it's coming in, the arms will close, go flush against the side of the vehicle, and the vehicle will be descending through the arms. And those tiny little, you can barely see them, the little knobs, those kind of lifting lugs will touch the top of the arms, and then it will hopefully not shear off and crumple. Success is one of the possible outcomes. The probability is uncertain, but it is above zero. I mean, if things are going right, it will actually look like the rocket is descending between the arms for quite a while. Yeah, I'm told this is the tallest thing south of San Antonio. We've already produced the first, and we have on site the first Starlink 2 satellite, and it's 7 meters long, and Falcon has neither the volume nor the mass to orbit capability required for Starlink 2. So even if we shrunk the Starlink 2 satellite down, the total up mass of Falcon is not nearly enough. I think what really matters is what's the total useful payload to orbit per year.
Yeah.
Because otherwise you could say, if this were ocean ships, you'd be like comparing a dinghy to a supertanker, and it's like they're not the same. For a satellite constellation, the thing that really matters is what is your total mass flux, useful mass flux to orbit. Yeah, so we need Starship to work and to fly frequently, or Starlink 2 will be stuck on the ground. I mean, the Starlink 2 satellites are almost an order of magnitude more capable than Starlink 1. Useful bits data is almost an order of magnitude better than Starlink 1. User terminals work with Starlink 1 or Starlink 2 satellites. 2s are just much more capable. It's insane. I mean, the ship looks small from here. This is not a good place if you have a fear of heights, that's for sure.
Either that or you'll get over them real quick.
Yeah. We should get like a hang glider and jump off or something. I mean, you could probably zip line pretty far. For the first time it is possible, that's a possible outcome to make life multiplanetary. The key to making life multiplanetary is a fully reusable rocket. That's the key. It's just very hard to achieve full reusability given the strength of Earth's gravity field and the density of the atmosphere. Full reusability is like relatively easy on Mars, which has around 37-38% of Earth's gravity and about 1% atmospheric density. But it's just barely possible to achieve reusability on Earth. Like, it's not as though, all the rocket engineers in the past, it's not as though reusability never occurred to them. They're well aware of aircraft and other things. It's just that it's an incredibly difficult technical problem. They just thought it was impossible, or the probability of success was so low that it was not worth doing. If you think really long term, then you realize that eventually there will be some natural disaster, even if it is not made by humans, that destroys all life on Earth. So eventually the sun will expand and evaporate the oceans, and we'll be like Venus, so hot that no life can really exist, or maybe some chemotropic bacteria, but eventually even they will die. So the only way to prolong life as we know it is for us to become multiplanetary and ultimately multistellar. If we do not do that, all life on Earth will die. So those who care about life on Earth should really care a lot about life becoming multiplanetary and ultimately multistellar. Earth does not currently have any ability to stop asteroids. Now with Starship, that we then have some ability to stop an asteroid. Actually, technically a comet would be the real danger, because there are billions, if not more than billions, maybe trillions of objects that are in the outer solar system, some of them with that are very long period comets. An example that most people are probably aware of is Halley's Comet. So I forget the exact periodicity, but it's slightly under once per century that Halley's Comet comes by. So there are probably many comets that have very long periods that we simply don't know exist. For example, the comet Shoemaker-Levy, when that hit Jupiter, it made a hole in Jupiter the size of Earth. So if that did hit Earth, it's game over. Everything's dead. The probable lifespan of life is just much greater if we're a multi-planet and ultimately multistellar civilization. The economy is very much a positive-sum game, a kind of a growing the pie situation. When people examine their understanding or beliefs of the economy, if they have an implicit assumption that the economy is zero-sum, then the only way for one person to get ahead is by taking things from another. But obviously the economy today is much, much greater than it was in the past. The economic output per person is massively greater than the past. So obviously what has happened is that the pie has grown, and it has grown much faster than the population has grown. If one creates wealth or create great products and services, that is something that should be applauded. That is effectively increased the standard of living of the country and perhaps of the world. Sometimes people will think of consumption and wealth as the same thing, but they're obviously not the same thing. Consumption is fun, but capital allocation is a job. Anyway, I don't think a ton of people want Warren Buffett's job, which is to read through very tedious annual reports of companies, including the minutiae of the accounting, and decide whether to invest in Coke or Pepsi. I don't want that job. Air travel used to be accessible to very few people. It was insanely expensive and dangerous, and now it is commonplace to fly somewhere.
Wow.
It's a hell of a lot of progress. The propellant storage for the whole vehicle was actually quite difficult. Put a lot of effort into the propellant storage. For Falcon 9, for a while there I was living out at the Cape, getting all 9 engines to start and take off, and because we would just have one launch abort after another. And I brought the kids with me, and I went to Disney World a lot and Harry Potter Land.